My name is Nader Haghighipour. I'm a professor of astronomy at the Institute for Astronomy, University of Hawaii, and also a senior scientist at the Planetary Science Institute. My research is about understanding the formation, characterization, and dynamical evolution of habitable planets in our solar system and in the extrasolar planets. I try to understand how Earth formed, how water came about, and then apply that to other extrasolar planetary systems to understand how habitable planets around other stars come about and what to look for when we want to identify their habitability. I also try to understand the formation and characterization of planetary systems that have more than one sun. Planets in binary star systems, either planet around one star of the binary or the planet going around the entire binary system. I try to discover them. I try to understand how they form, what is the dynamical evolution, and also try to understand whether they could be habitable, and if they are habitable, how to detect the signature of life on them. I work with a variety of different groups for my work on planet formation. I work directly with my colleagues in Germany and in University of Vienna. We work together to understand the collision of objects and understand how these collisions result into accretion and growth of the bodies. And in regard to extrasolar planets and planets in binaries, I work directly with my colleagues at San Diego State University and also at Goddard Flight Center in Washington, D.C., where we analyze data from Kepler mission and also from TESS telescope to identify eclipsing binaries and then use that to identify planets around those binary systems. The launch of JWST, James Webb Telescope, is of utmost importance to the research that I do. And the reason for it is the following. During the past 25 years, our team have been able to identify planets that could be potentially habitable. Two of those planets were actually discovered here in Hawaii using Keck telescopes. One planet is Gliese 581G and the other one is Gliese 677cc. These two planets are slightly bigger than Earth, however, they are exactly in the habitable zone of their star. And if they maintain water on the surface and if they maintain the right atmosphere, they could potentially be habitable. What JWST does for us is that it could use these two as two of its targets and look towards these two planets. And given its sensitivity and its being a big telescope, it will be able to identify the signature of water molecules in the atmospheres of these planets. If there is water molecules, JWST will certainly be able to identify those signatures of those water molecules. And just with that, we'll be able to say whether those planets have the potential to become habitable or to be habitable or not. Whether JWST has already decided where to look to identify the signature of life has not been finalized yet. So far, what has been done is that JWST went on its orbit, settled in the orbit, opened up the panels, and sent the first light showing that it actually works. Now, what's going to happen next is that as engineers go through all the process to make sure that the telescope is stable and is producing the reliable result and data, then comes astronomers, and that they will be the ones that they're going to use the time on JWST to search for signatures of whatever they want to do around different stars or different galaxies, whatever they want to look at. So, point being, there will be a time after all this engineering and everything is done, there will be a time that the time of the telescope will be open to astronomers, and astronomers can apply for time to look into specific targets. And once that becomes available, these two stars these two planets are two of the targets that we are planning to look into. Water would be a good tracer for possibility of life, but JWST will be able to identify other components as well, CO2, CH4, like carbon dioxide and methane gas. Methane gas would be a better indicator of life as well, because if life similar to Earth life exists on another planet, that CH4 is one of those byproducts that will certainly exist. CO2 is because of the internal dynamics of the planet. CH4 is because of living entities. CH4 is produced by living bodies, not necessarily us, but by animals and others. So living entities that actually live on the surface of the planet will produce methane gas, and that will be not only will tell us that the planet is habitable, it also tells us about the possibility of the type of methane producer organisms or entities on the surface of the planet. At the moment, there is no set time that when the time on JWST will be available, and what we know is that the telescope is working, that it is settled on its orbit and everything, but when the telescope will be available, similar to Hubble, when it will be available that we can actually write proposals, get time on it, and give the targets to it, still not determined. Once the targets are identified, then soon the telescope will be able to capture what. Of course, there's also noise, so it's not going to be that with one shot you get what you want. You have to identify the noise and how long you need the telescope to sit on the target, and all that. So all that process will go through, and but we are hoping, and what is for sure is that it will be faster than what Hubble has been doing. First results were absolutely fantastic, and when you put them next to Hubble, Hubble was the masterpiece when it went up there and produced all these detailed figures and photos of what ground-based telescope were struggling to identify. And now JWST goes up there with much higher resolution and determines and identifies details within Hubble pictures that Hubble was not able. So it is much, much, much better. And but it's not unexpected. This is what it's supposed to do. It was supposed to go up there and produce photos and pictures much more with much higher resolution and much crisper than Hubble, and it succeeded to that. So when we got those, we're like, yes, that's exactly $1 billion is supposed to do for you, you know, and that was the huge success, and made the entire astronomy community happy. All data that are gathered by any space-based or ground-based telescope, they are all archived and they are available to public as well as astronomers. It depends on the type of the telescope. Some telescopes open it to public, some telescopes keep that available to astronomers for a certain number of years and then open to public. But in general, all data that are gathered by any telescope, they're all available to the astronomers, to scientists, and general public for the analysis. JWST will be like that as well. But how long the data will stay before it is released to public, I still don't have a good handle on that. But given that any telescope, including JWST, they are all supported by taxpayers' money, that data will actually go back to taxpayers even if they are not astronomers. My direct students or postdocs that work with me, they may not be able to, or they may not be, the field may not get them into using JWST, but I have a strong feeling that once you get to the field of habitable planet formation, planetary formation, all that, eventually you will be working with people who use JWST to produce data that would be useful to your modeling. Receiving all the data from a big telescope like this, and then processing that, and then get the science that you want, that is an industry by itself, and many people get their PhDs on that. Same thing happened with Kepler. When Kepler, the data started coming, there was a large group of people that their job was only to receive raw data, process that, identify light curves, and archive them so scientists could use them. And same thing with JWST. There is a large team of astronomers and data miners and data processors and engineers whose job is to get the raw data and process that in a way that astronomers will be able to use them. So, like I said, it's one industry entirely by itself. People get PhDs and postdocs in it, and they get permanent positions in there. And most of those positions are associated with places that support the telescope, like, for instance, NASA. And all their job is to just receive the data and process it. So it is difficult, but because their expertise is that, we rely on them 100%, and we know that what we get from them is exactly what comes out of the telescope. Hubble was supposed to go up there only for 5 years, and has been there for almost 30 years, and there is no end to it. It's going and going, right? So if Hubble was doing that, and JWST being much more advanced both technically and as far as resolution, we are in for a long haul. You know, I'm hoping that for next 25-30 years, we'll be able to get very good, useful results from JWST. JWST not only will give us clues to the origin of the universe, how universe formed, will also tell us more about extrasolar planets. So when the field of extrasolar planets started 25 years ago, we were limited to ground-based telescopes, and most of the observations were done either at the Geneva Observatory or here in Hawaii using the Keck telescope, or in California using Lick Observatory. These were the biggest telescopes at that time. And when Kepler went up into space, after that test, the number of the discovered planet became so large that the field, in a very short time, the field went through a huge, fast pace of progression and became one of the most subtle and progressive field of science, not only astronomy. Now extend that to JWST. What JWST is going to do that astronomy is that it's going to provide so much data that what Kepler did to planetary science JWST is going to do to galaxy astronomy, stellar astronomy, there's going to do the cosmology, and to extrasolar planets. So we are going to see huge advances in all fields of astronomy, and especially in the origin of planetary systems, origin of the universe, in a very short time. And that is what I'm very much looking forward to.